This video will introduce you to Bayesian belief networks. It's supplemented in the course materials with a second video that shows you how to use Netica, a Bayesian belief network software package. These are our modest objectives for this video. At the end of this session, you'll be able to define a Bayesian network, identify conditional probabilities, lay out a simple belief network model, and provide probability inputs to a simple model. A Bayesian belief network is a special type of graph that consists of nodes and arcs, as shown in this simple example. When used together with an associated set of probability tables, they enable us to model and reason about uncertainty. Our simple example describes a scenario by which internal erosion could cause a levee to fail. Estimating the probability of a levee failure is a daunting challenge. Trying to estimate the probability of levee failure under a wide variety of circumstances could be incredibly complex. Even the simple roll of 2 dice requires us to account for 36 different outcomes. Imagine if the probability of a green 1 was different from the probability of a green 2, and so on. This would yield different probabilities for each of the 36 outcomes. The world grows quickly complicated. A Bayesian belief network helps us generate conditional probability distributions in a simple and straightforward way. Let's build a simple model of levee failure. We begin with roots in the levee, and then we'll add animal tunnels which can contribute to interior erosion of the levee. In this example we're building, the outputs of interest include whether the inspection picked up the presence of interior erosion or not, and did the levee ultimately fail. We use arrows or arcs to show how the variables are related in our model. We'll be using this model now for the remainder of the video. In a Bayesian belief network, the dependencies between different variables are made explicit using arcs between nodes of the network, as shown here. Often there are relatively few direct dependencies. This means that many of the variables are conditionally independent. In the simple example here, the nodes inspection and levee failure are conditionally independent. Notice there is no arrow or arc linking them. Once the value of internal erosion is known, knowledge of inspection does not affect the probability of levee failure, and vice versa. These unlinked or conditionally independent nodes in a network drastically reduce the computations necessary to work out all the probabilities of levee failure or inspection results that we require. All the probabilities we're interested in can be computed from the joint probability distribution using Bayes' theorem. An example of such a conditional probability is given as shown here, where we have the probability of levee failure given that roots equals true, animal tunnel equals false, internal erosion equals true, and inspection equals false. The joint probability distribution is much simpler to compute when there are conditionally independent nodes. With 5 dichotomous nodes, like we have in this model, there are 32 conditional probabilities to estimate. If the number of dichotomous nodes increases to 8, there would be 256 probabilities to estimate. This makes a Bayesian belief net a very powerful and useful tool. Bayesian belief networks are useful for a wide range of uncertain situations. The example we'll be using here is based on the failure of a levee. This screen capture from a National Flood Insurance Program webpage provides a vivid photo of what a levee failure could look like. Although levee failure scenarios are numerous and diverse, we'll use a simple one with these 5 variables. Variables can be continuous or discrete. It's far easier to work with discrete variables to learn about Bayesian belief networks, so all 5 of our variables are discrete dichotomous variables that are either true, that is, the condition exists, or they are false. Roots means there is a significant presence of roots from woody vegetation in the levee itself. Animal tunnels means there is a significant presence of animal tunnels in the levee. Internal erosion means the interior of the levee has begun to erode. Inspection means that an inspection has indicated that internal erosion is likely. And levee failure means the levee has failed to function as it was designed to do. Each of these variables has the value true or false. This summary summarizes the nodes and their values. Notice on the left the 5 variables: roots, animal tunnels, internal erosion, inspection, and levee failure. The type of value is Boolean. This is the same as dichotomous, as we spoke of in a previous slide. And the values for each of these is either true or false. So the challenge, if you're building a Bayesian belief net, is to choose values that represent the world efficiently, but that have enough detail to enable you to perform the reasoning required and to calculate the values that you seek. Let's talk a little about the structure of this model. Models begin with parent nodes. Parent nodes with no parents are called root nodes. And with root nodes, you only have to assign 2 probability values, either true or false. With all the other nodes, the number of probability values increases, as we'll see in a later slide. A child node has parents. A child node can also be a parent to another child node. A node with no children is called a leaf node. Arrows show the direction of causality in the model. In this example, the presence of animal tunnels can affect internal erosion. Root nodes are immediate causes. Intermediate nodes are often quite common in Bayesian belief networks, and leaf nodes are the final effects in the model. Let's summarize briefly and consider our next steps. To build a Bayesian belief network, you begin by identifying the problem, and then you proceed to identify the nodes in your articulation of the problem. The nodes are the variables that are important. Next, you determine the values you're going to use to describe the nodes. Are they discrete or continuous? The cause and effect relationships or topology of the model is next. And then finally, you have to quantify the relationships between the connected nodes. And this means to estimate the conditional probabilities. Let's look at how you would quantify a model like this. First, recall that we're using discrete variables. This significantly simplifies quantifying the model. The values that you see on the screen are the calculated true and false values for each node. You would enter the values in the root nodes, but the other values are calculated for you based on the data that you would enter. So let's quickly review to make sure we interpret them the same way. This model says that roots are present 30% of the time. Animal tunnels are present 90% of the time. Internal erosion occurs 3.31% of the time. 12.3% of all inspections report internal erosion, and levees fail 0.18% of the time. All the data here are hypothetical and were made up for this video. The model you're looking at, and much of the discussion that follows, relies on the use of Netica. This is a Bayesian belief network software system that's available free from the internet, made by Norsis. Notice the 2 root nodes at the top of the screen. As I just mentioned, these are the only variables you have to enter data for directly. All you have to do is provide an estimate of the true and false values for each of these. Notice in the screen that there's a 30% chance that roots will be a problem and a 90% chance that animal tunnels will be a problem. Now let's move on to the internal erosion node. because it has two parents, there are four possible conditions for its two parents. And these are true, 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 false, false, true, and false, false. Now let's suppose that the parents, or the conditional information, yields a true, true situation. What's the probability that there is interior erosion? Well, you can see here that there is a 5% chance that there is interior erosion when there are roots and animal tunnels present. There's a 95% chance that there is no internal erosion. Now let's take a look at the situation where we have a false false for the parents. There are no roots, there are no animal tunnels. Here we see the probability that there is an interior erosion problem has dropped to 0.1%, while there is a 99.9% chance that there is no interior erosion problem. In a similar manner, interior erosion is apparent to the last two leaf nodes, and they require two different conditions each. So if there is interior erosion, the probability of failure is 5%. If there is no interior erosion, that probability drops to 0.01%. When there is interior erosion, we see that the probability that an inspection will identify it correctly is 80%. There is a 20% chance that an inspection will fail to identify the interior erosion. Similarly, when there is no interior erosion, the inspection will report it as present 10% of the time. That would be an incorrect diagnosis. 90% of the time, the inspection would correctly identify no interior erosion when there in fact is none. How do you estimate the kinds of probabilities you see in the table here? You use the best available data. In this case, the National Levy Database would be that source of information. And then you would supplement it as needed with expert elicitations. There are a few points to understand about this kind of model. One of them is that although you can have more complex dependencies than seen in our simple example, you cannot have any cycles in the model. For example, you cannot have roots influencing interior erosion, influencing inspection, and influencing roots. The Markov property is also assumed to hold for the model. That means that all direct dependencies in the model are represented by the arrows. By the way, notice that the probability of levee failure is 0.18%. We're going to use that in just a moment. Once the basic model is built, we can observe how the probabilities of other variables are affected as the information available to us about uncertain values changes. This enables us to use the model for probability propagation, inference, and belief updating. Suppose we learn that a levee does have significant roots present. Notice that the probability of levee failure has increased from the 0.18% I asked you to remember to 0.24%. So knowing that there are roots present changes the probability of levee failure. It changes the other probabilities as well, but we'll just be focusing on the levee failure in the next few slides. Now suppose a levee has significant roots and animal tunnels present, as shown in this graphic. Notice that the probability of levee failure has increased from the original 0.18% to 0.26%. Suppose we learn that a levee has roots and animal tunnels present, and the inspection identified interior erosion. Notice that this information increases the probability of levee failure to 1.49%. So information changes probabilities, and a Bayesian belief network can be used to show just how that happens. Bayesian belief networks support different types of reasoning, including these four. Diagnostic is reasoning from symptoms to a cause. Predictive reasoning takes you from new information to new beliefs about final effects. And intercausal reasoning examines mutual causes of an effect. Then there can be combined reasoning, which involves two or more of the above kinds of reasoning. Diagnostic reasoning begins with the levee failure and works backward to the causes of the levee failure. Here's an example of predictive reasoning. It takes into account all the variables that can affect the probability of levee failure, and it makes the prediction of the levee failure probability using that information. Intercausal reasoning takes into account all the factors that influence an intermediate node. Not shown in this video is an example of combination reasoning. What we want to do is to calculate new beliefs as uncertainty is reduced and new information becomes available. The U.S. Army Corps of Engineers National Levee Database includes data on 3,000 non-federal levee systems that produce information that will enable them to continuously update their beliefs.